All right, folks, I will get started. So this is our lunch slot for the presentations. My hope with this talk is it's entertaining and a bit light. Um, so yeah, I'll introduce myself. I'm Nathaniel. I'm a uh, kind of adjacent to ArduPilot in my regular work, but I've relied heavily on ArduPilot over the years, and I've really grown to love it and used it. And now at this point, I'm starting to become a small-time contributor too to the project. So yeah, my talk today, I really want to focus on one of my main outputs for my work with ArduPilot, which is around using uh, ArduPilot Gazebo to do prototype design for our aircraft systems. So a little bit about me first. Can I just hold this? A little bit about me first. I'm a mechanical engineer by training, and over the last 8 years or 9 years, I've tried to pivot more into robotics control and systems. So uh, in my research work, I've really done my core focus on reinforcement learning, optimal control, multi-agent swarming systems, and engineering design. Uh, my day job is I'm a engineering manager for the company I work with named Romeris. And what we're trying to do is develop a new type of plane UAV system based on hang gliders and air trikes. And I'll explain a bit more about that pretty soon. Um, my PhD work centers around my work with the company, where we've developed a world first adaptive flight control for these UAV systems. And just to call it out, this is my 7th year now of using ArduPilot for my development work. When I started, I really didn't have a clue what I was doing. I wasn't a classically trained software developer, so there was a steep learning curve to pick up how to program real-time systems with C++, especially for control of, flying systems. So yeah, it's been a long road. That's me there with my my Hexoon TD900. My other activities all these days kind of center around tech development. So just calling them out because I think if you have any interest in collaborating after the fact, um, I'm a program coordinator for a training initiative at a university in Ottawa, where I'm from. I'm a technical lead for a consortium where we're trying to work out how to do greenhouse gas emissions detection using drones and correlating that to satellite data. Um, and we're looking for new partners for that. So if that interests you, please talk to me afterward. And recently I got offered a small-time tech fellowship role with a venture capital startup incubator in Montreal. So I have a bit of reach now, which is nice for my work. With respect to my work with ArduPilot more recently, just to call them out, we've done work now doing greenhouse gas emissions detections where we mount a methane sensor onto a drone and we fly patterns to try to characterize like gas plume distributions. So that's one example there. And then for some more recent development work we've done for ArduPilot, we're trying to take the bendy ruler avoidance algorithm scheme that was used for the Outback Challenge in 2018. And we're trying to convert it to use more like a Lua scripting framework. So if you're familiar with like the ship landing feature in using Lua, we're trying to use that as our example to start with and then build out the old plane avoidance features using bendy ruler as a Lua script or a set of scripts. So at this point now we have the obstacle generation working. We can communicate between ArduPilot and Lua to discuss obstacle state. And we're able to see if there's clear to proceed versus if there's an obstacle in the way. And now we're trying to work out how to do the actual avoidance calculations and control using Lua. And so that's what we're working on now. Okay, so to my development work, this here is our electric unmanned weight shift control aircraft. So when I say weight shift control, I'm talking about like hang gliders or air trikes. So completely different than the normal fixed wing planes that most of us use for ArduPilot. Um, why these? It's just flat out, no one's done it. And we think that they have some pretty interesting qualities that are worth developing for or to use eventually. So uh, they're extremely low cost. They're extremely low maintenance. They have long range, being a larger plane, and high endurance since they're a glider. And you can also maneuver them at low speeds thanks to their weight shifting control and the large kite wing that is on top. The challenge with these aircraft, though, is it's very difficult to model a flight control, partially because nobody's done it, and the aircraft dynamics themselves are quite nonlinear. So let me explain what I mean by that. These aircraft, like I said, they don't have control surfaces. It's a big kite, and you're shifting your mass underneath to try to change your attitude. And you're moving your mass sitting in the seat under the wing in free space. So you grab the bar, and you're literally doing like this. So it's a completely manual control. There's not yet fly-by-wire systems to control aircraft like this. They just flat out do not exist yet. And part of the challenge that the company perceives, company being Ramirez, is it's tricky to learn how to fly these as a pilot. So even if you're an experienced or seasoned fixed wing pilot, when you then go and try to become a weight shift pilot, it takes tens or 100 hours just to convert your pilot brain from fixed wing to weight shift fixed wing. And a lot of it is fly by feel. Putting that in a technical way, there's substantial time delays to the control, and you have to be precise. So you can't be too slow and you can't be too fast. You have to be just right, to put it in a fuzzy sense. Flying these is a lot like driving a motorbike. Like you have to kind of lean into your turn and then lean out to turn correctly without falling over. And that's actually a challenging control problem. So just to drive the point home, here's an example of a banking turn. Your pilot applies a force on the control bar. You shift your whole mass under the wing one way. And then after a couple of seconds, the wing starts to rotate and you initiate a bank. It's a bit more complicated than that, but that's the basic idea. You're creating an imbalance that causes your attitude of your wing to change. And then you have to get yourself out of that changing imbalance that you just started to put yourself back into a balanced state or a trim state. So our development, it was tricky. It's like, no one's done this. There's no hardware for it. There really isn't much literature on it because no one's done it. How do you start? And so we have experimental and shop efforts, but part of the problem is it's expensive. We can't take a big risk you normally could for prototype development because we're not quite sure how to do it and we don't want to wreck our wings. And in the case of manned aircraft, we can't put the pilot in harm's way. So one idea was obviously, can we use simulation to replace flight testing and development? And the answer obviously is no. You can't just simulate your aircraft and say, yeah, that looks good. It'll work in real life. You just can't match everything that reality will throw at you. But it does present an opportunity, which is you can refine your models as you go over time to try to get closer and closer to real life. And what I really like about this approach to like dynamics simulation is you're not so much worried about a top level design, trying to just say, do exactly this. Rather, you're trying to come up with all the ingredients or pieces of your dynamics environment or the models that all work together. And through their interactions, you end up with something more complex or sophisticated. So the flight dynamics in the case of our weight shift models is sort of an emergent property of our approach to dynamic simulation. So if you're familiar with Gazebo, it's de facto the most used open source dynamic simulation for roboticist. But most of the time they use Gazebo for ground robots or stationary like multi-link robots. It's not as commonly used for flying robots. But what's really nice about Gazebo as like a developer tool is it's open, it's extensible, and with the recent upgrades they've done to their newer versions of Gazebo, the software architecture is far more modular than it used to be. So how I understand it as a mechanical engineer who does a little bit of development using Gazebo is the newer version is much more easy to support over time and use than it was 10 years ago. So as an example, if you haven't seen this, I strongly recommend searching this after my talk. But the ArduPilot community has done work on using ArduPilot CIDL with Gazebo. And so in a nutshell, you use lockstepping to make sure your Gazebo environment dynamics are in step with your flight control CIDL simulation. And this kind of gives you a way to actually do more sophisticated simulation than you otherwise could with just ArduPilot CIDL on its own. So this is from the ship landing demo page. So it's really cool. In a nutshell, they use a VTOL and they fly around a boat and the boat's rocking on water in simulation and they try to land it. And there's also some communication between the boat, which is running ArduBoat, and the VTOL plane to kind of coordinate at least the orientation of the plane relative to the boat. So in my work, I ended up contributing this model for a weight shift aircraft or an unmanned weight shift aircraft, UWSC for short. And it flies just with base ArduPlane. There's no additional control sophistication required to get this model to fly. And what was especially nice about this work is we were able to validate at least the dynamics that the aircraft model is approximating with real flight data that the company was gathering from manned recreational flights. So we were putting a, here. Well, before that, I just want to say if Reese is listening, special thanks. He really helped out with this work and kind of helping me get up the learning curve. And not only that, I think he's been kind of the sole Mac OS Gazebo developer guy the last few years. So big shout out to him if he's listening. And if you know him, tell him I said thanks. Yeah. It doesn't seem all that impressive as a picture, but this is the first time anyone ever has implemented a navigation controller for a weight shift aircraft. Like, it doesn't exist until this. So yeah, in a nutshell, we're using the L1 and text controllers. We're driving state information to pick general reference angles we want to hit. And then we're relying on just the feedback to actually fly the aircraft. So it plugs right into basic ArduPlane. I want to stress that point. You could try this today if you want. And what's important to highlight is unlike the fixed wings with control surfaces, the tricky part is our control has to move a pendulum swinging underneath the wing in a certain way. So it's a little more tricky from like a dynamics perspective than what you would normally just say, here's my model for my control surface. And if I do this much command, I'll get this much response at that speed. So just before we get too into it, just a little video break. I wanted to pull this up just to show an example of like a city environment in Gazebo. And we're flying little planes, like a demo mission using Gazebo, or maybe you have some visual sensor of some kind. So then here's the unmanned weight shift control model moving the pendulum underneath in roll, then in pitch. One of our validation missions. So we took 13 sets of mission data and we said, hey, try to fly roughly that track. And let's try to compare the dynamics that come out of that. Or not the dynamics, sorry, the logs that come out of the simulated mission and compare it to what we got from our real life avionics. Here's some new work we've done for our greenhouse gas consortium, trying to just demo, hey, if we put a sensor in Gazebo, we read a gas cloud as we fly through it. And so, yeah, you get through the cloud and you get a little spike. Here's another one. We have multiple aircraft all flying at different altitudes to try to say, how does the gas measurement change as you go away from the emission source? And lastly, here's kind of the long-term vision. If I have a whole bunch of really cheap planes with long range with gas sensors, can I just drop them into an area of operation and coordinate their flight to characterize whatever's going on in the area of interest rapidly? So that's kind of the long-term vision I have for that work that I'm trying to do. So each of those lines is a trajectory being drawn by a plane. To the presentation. Like I said, we flew real flights and we put ArduPilot on the aircraft in just like a monitoring mode. And we collected we collected logs from the flight. And we used that to validate our simulation model's accuracy. So here's one sample. We actually track quite close in both the altitude and the 2D ground track projection. And that held for the majority of our missions. Here's a comparison of parts of the 13 flights all put together. So a level section and then turning sections that we defined, just to show, hey, yeah, whenever we have these two parts of the flight that we care about, how well do we track them? Landing and takeoff. So you can see a divergence here. In the case of takeoff, since it's automated and simulated, the takeoff is like perfect each time in Gazebo, whereas in real life, there's variance from the human pilot. And then for landing, different problems. The landing approach depends a lot on just how the pilot decides based on the wind conditions to descend and then slow down and touch down. And then using Gazebo lets you do crazy stuff. So in my work, my primary focus for my PhD project at the beginning was implementing an online reinforcement learning scheme. I won't get too much into it, but in a nutshell, the controller I'm really proud of takes a simple combination of dynamic stability and tracking error information and combines it together into a set of information that then your online reinforcement learning learns against. And this online reinforcement learning algorithm is implemented directly on the flight controller, on a NavIO or Raspberry Pi with a NavIO too. So doesn't take much. And the reason that works is because we're using something that's not super commonly known called temporal difference learning. And it's based in a type of theory called approximate dynamic programming. So I just wanted to call this out because I think there's a lot of attention on learning where you need a big, heavy GPU and a computer and offline training and like 100 hours on a stack. And these methods are meant to be used in real time. So you could incorporate a learning agent with your control to try to suss out some particular behavior that eludes you. So with reinforcement learning, I just want to be clear, it's not a magic bullet that just does control better, nothing like that. You really use reinforcement learning when you want to try to do more than just solve an error. So if you're trying to balance multiple objectives like hey, I want to keep my airplane in the air, but I also want to try to track air somewhat. So like here's an example. We put an experienced pilot on the sticks in simulation. And on the left side, you can see this is their roll track. And on the right is the evolution of the agent weights for the roll controller. And it flies okay. It tracks well enough. There's saturation conditions that we try to avoid, but as you can see, it exceeds them and then comes back. Saturation limits on the roll state that we want it to be allowed to have, but it keeps the aircraft in the air and follows what the inputs are. Meanwhile, for our pitch agent, the other controller, because we only need roll and pitch to fly these things, it kind of learned pretty quickly, hey, don't follow the pitch reference angle the pilot's giving you. It's junk. There's a limit on it too. So instead, I'm going to try to just fly this thing and take the pilot's input as a suggestion, which sounds weird, but I remind you, the whole point of reinforcement learning is not to solve errors, it's to just balance multiple objectives. As long as you can define what you mean by an objective mathematically, you have data, maybe you get a result. To the real meat of the presentation. This last year, we had a really big challenge, which was, God damn, it's hard to actually develop prototypes of full-size 100 kilogram plus aircraft that are unmanned. Big challenge. We're not at that scale yet. So we pitched, what if we made a miniaturized version? No one's done this. The closest is there are RC models, but the RC models don't have formal analysis, and there sure isn't ArduPilot solutions for those RC models. Or if there are, I'm not aware of them. So now we've done that. Again, I just want to remind you, part of what makes flying these aircraft difficult is you have these air elastic properties of the wing that kind of dictate how the sort of the aircraft responds as it flies and changes speed. So yeah, the challenge was, how do we scale this to different scales? How do we make unmanned weight shift control aircraft at big scale and at small scale and in between? And thankfully, because of the simulation framework we developed using Gazebo with ArduPilot Siddle, it really helped accelerate our prototype development. So just to remind you, you define your geometric, your mass, your inertial properties of your aircraft. To size the wing, we used a program called XFlyer5, XFLR5. And then based on the aerodynamic results of XFlyer5, we tried to map it to the really rudimentary lift drag plugin that's in Gazebo. We sized the pitch and roll actuation to try to match our real servos that we were using for the prototype. And finally, we put ArduPlane on it. And we just followed the ArduPlane default setup process. There's no other tweaks. The closest thing to like a tweak would be, there are things you have to do to the parameters slightly differently to get it to fly more like a weight shift aircraft compared to like a fixed wing. And doing that, you can get a prototype that flies pretty okay. I think there's work left to be done on trying to say, okay, what other adaptations to the control do you have to do to support different parts of the flight envelope for your weight shift aircraft? But good news, if you don't mind having a highly performant aircraft, you just want it to fly at like low roll and pitch angles and reasonable speeds, you can pick a set of PID gains that works, and you should be set. So yeah, back to the development of our prototype. The initial maiden flight of our aircraft was based off a auto tune in Gazebo. So we took the model, we auto tuned it. We said, okay, what did it spit out? And then we said, we're kind of scared of some of these parameters it spat out. So how about we make them a little bit more conservative or weak? And it flew. It flew fine, not great. And we could keep it in the air though, which was impressive. On our first attempt, we kind of developed what we called our input replay script. And the basic idea is we took the literal RC input from the pilot and we just fed it back to Gazebo, trying to match it to real time. And really crude, it needs more work, but that's what you're seeing here is the RC input of real life to simulation. This method will work, but to a point, because as you continue like your simulation of your dynamics, eventually what you simulate will diverge from real life. It's just a fact. It's too hard to match things precisely unless you have an excellent model and really good feedback control to keep it where you want it. So here's like an example from our first maiden flight, comparing it to then a simulated version of the maiden flight. So I want to really highlight or stress that we're not, the only thing we're giving the sim is just the RC inputs. Otherwise, the sim model is just doing what the RC input says to do. And yeah, it follows the dynamics reasonably well. So like speed, same shape, different magnitudes. Altitude is almost perfect, which was nice to see. And then pitch and roll are pretty close. The roll looks kind of funky, but that's only because, sorry, the top right one, that's only because the roll angle in real life went over 180 at one point. Here's one example that was really fun. We did one flight test of our prototype and we flipped it. We took off, we put too much throttle on it, and the thing flipped. Not great. And so the question we were sitting around scratching heads, and it's like, what did we do? Like, why did it flip? We haven't flipped it before. We've done the takeoff kind of the same each of our flight tests, but that time we flipped it. Were the winds bad? And our hypothesis that we were working with was maybe there's just too much throttle. Like maybe the throttle is oversized, or the thrust, sorry, and the pilot used too much throttle. So instead of kind of head scratching, doing some napkin math and then trying it again in real life, we said, how about we test it in simulation first, just to confirm. And sure enough, we do input replay, and we're able to match the dynamics of the flip. For me, it was a shock. Like, I didn't think the crude lift drag plugin in Gazebo could do stuff like that. I thought it would just say, oh, you're fine, keep climbing. Like, go pitch up more. So yeah, satisfying to see. So that's like a front view and that's a side view of the same loop. And they line up pretty well. So then we say, well, let's just drop throttle, put a limit on it, see what happens. So now what you're seeing is a before and after. So before is our previous figure of the two loops in sim and real life. The after is the simulated loop if we apply the throttle limit. And what do you know? It takes off and it kind of floats and then it hits the ground. Great. If we had done that, our flight test would have been great. We wouldn't have done a flip and hit the ground. So we did it. That's what we did. We put that in real life. And what do you know? It saved us a whole wasted day of flight test, damaging our aircraft, having to repair it. So the cost saving, both in like time and money, is immense. So yeah, I can't talk too much about the development, like the flight test campaign from this year, but it's been very successful for us. We've gone from a simulation model that we cooked up in November of last year. And this summer, we've gone to a point where we have a totally novel prototype of this aircraft flying in auto mode. And what we're trying to work out now is how to do auto landing and then auto takeoff. And if we can do that, that's a workhorse. We can probably go do revenue jobs with it. We can go show it off. So I want to really stress to the room of developers or interested parties, I think the use of Gazebo or equivalent dynamic simulation with ArduPilot remains untapped. And I understand part of that is there's a steep learning curve and the utility of it might not be clear. But for us, what it's provided us is an essential tool to make our development more rapid. And that's because it gave us a way to do initial tuning. We can do post-flight analysis using simulation, and we can even consider different case studies. in sim rather than in real life. And so yeah, on the left side there, it's just from last week. We did an auto mission and then an auto land attempt. It's hard to see on this like that. I'll post it in Discord later, but I'm really proud of that image. It flew great. Our L1 controller needs tuning, but it tracked the waypoints, it kept altitude, and then it almost landed really well. And if you've worked with auto landing, you know it's a little tricky. So, um, so video break number 2. Just a little demo reel. Here's the full-size prototype we developed a few years ago. Before we went into the challenges of how are we actually gonna get this thing to fly autonomously. Here's a equivalent prototype floating, doing state regulation. So I want to show that a bit more. On a beach in Mexico, and we're basically just letting it float off wind coming from the ocean, and ArduPilot is controlling the robotic actuators to kind of keep it still in space. Here's it rolling. This is from promo footage I don't care about. Looks cool though. And then here's the miniature prototype I was telling you about flying in the air. So I'll just let it play out. Here's FPV footage from underneath at our test track in Ottawa. A overhead pass. A for this one. And then here's another overhead pass in fly-by-wire B. So it's way off in the distance. The pilot's doing visual line of sight control, but it's in fly-by-wire B. So all he's really worried about is just altitude management and heading control. Whoa, sorry guys. What am I doing? Oh, shoot. Um, there you go. That's real time. And yeah, it's flying like a charm, just with base ArduPlane. So yeah, to come back to it, I just want to say thanks to Randy and Andrew or Tridge for inviting me to come to the conference. It's my first one. And then for the hotel staff for their hospitality, and for Kaga City for welcoming us and letting us enjoy our time here. And yeah, I have a few calls for collaboration. There's a whole bunch here to give them rapid fire. If you want to work on simulation-oriented prototype design work, that's kind of my bread and butter now. Provide data on drone delivery methods, or you have a connection. We have students at Carleton that really need help with data access. So if you know anybody, please do me a solid and come talk to me afterwards. We have room in the utility program, the training initiative I mentioned, for international partners. It's winding down over the next year and a half, but we're trying to think about what comes next. That's kind of the spiritual successor. So now that I'm hooked up with you lovely folks with ArduPilot, I'm hoping to find partners for that. We want to start exploring wildfire management projects in Canada. We're already doing science mission payloads through the NRC, and we have the Greenhouse Gas Consortium. So if you find that work important and you want to work with a satellite data provider from Europe, we have the connections. And then finally, looking forward, we're trying to develop detect and avoid systems that are low cost using sensor fusion methods. So that's to support our beyond visual line of sight development that we're trying to get up to. So if you're interested in any of those, please don't be a stranger. I made these cheesy little cards just for this. So come on by, say hi, and let's chat. Thank you. Questions? Yeah.
Fantastic talk. Thank you.
Thanks.
I was curious about what this vehicle would be like to fly in manual mode with RC, where you don't have the feel, the feedback in an aircraft like this. I've never flown one, anything like this. I've never flown a hang glider, but I imagine, like you described at the beginning, where the feel of the aircraft on your body is very important.
Yeah.
So have you done much flying of this in manual mode with radio control? And in which case, how hard or easy is it to fly in manual mode?
Okay. So I left it out because I wanted to focus this on unmanned applications. But the earlier development with Romaris was really on optionally manned actuation systems. So how do we do a fly-by-wire system or a robotic system to replace a human pilot? Basic math there is you take the pilot out, you put in stuff. You can do more with it. But the CTO of the company is a weight shift pilot himself. It's a hobby for him, really, the company. And we're trying to build a whole company around his hobby. So why I'm mentioning that is most of our bandwidth early on was just how do I make the fly-by-wire system give feedback? How do I make it feel so that I can sit there on the sticks? And the fact is, we don't have a way right now to give tactile feedback. So what we've had to do is develop force admittance systems for the full-size aircraft. So in other words, like a cable-driven robotic scheme that lets you vary the amount of force you apply to be a soft touch or a hard touch, depending on if you're in a really bad state and you need to get out of it versus if you're just trying to do a control and to remain gentle. And so doing that with like at a force control level has allowed us to give the RC sticks to a trained shift pilot and fly it. And so that's been our proprietary work on the actuation systems itself. But that wasn't through like an unmanned application yet. So then the other side of it is our work with this one, the M2, or sorry, the miniature prototype. And the fact is, when we first made the prototype and we gave the RC pilot control in manual mode, no less, not fly-by-wire A, and we said fly it, it was bad. He couldn't fly it well. It was hard. Part of the challenge is just like I mentioned earlier, you're not controlling control surfaces with a very quick response. You're controlling a big dumb weight and you're trying to jostle it around to keep balanced. So it's like a mix of an inverted pendulum and a motorbike, right? So manual mode, kind of crap. Maybe if you really get skilled with it, you could learn how to fly. But we said, no, this is stupid. Sorry, this is silly. Let's go to fly-by-wire A and try to rely on the built-in aero controller. And yeah, it flies pretty okay at limited parts of the flight envelope is the key. So we're not trying to do acro flights like what Andy was showing us yesterday. So is that roughly what you were looking for?
Yeah, it's sort of what I expected. And it's because one of the things that I would often do with a new aircraft is I would try to make it trim the aircraft so that it does fly reasonably well in manual mode and then apply the automation on top.
Mm-hmm.
But I was curious as to whether that methodology would work at all. And it sounds like it doesn't work well because flying it in manual doesn't give you the feedback you need.
No, so it could work if you had a really well-balanced and well-designed version of this prototype. So going back to the full size, the difference between a real cheap, like $10,000 one and like a $100,000 air trike comes down to make or quality of the build. And they put a ton of attention into wing balance and weight balance. And I know any aircraft system, that's what you care about, or plane system. But especially for these aircraft, if you don't balance those things well, that's the difference between a really nice, relaxed flight and a flight where you're sweating and you're working like you've never worked before. And if you don't hold on, you're gonna lose your strength and basically fall out of the sky. So that's for manned pilots flying manually. And so the challenge is really part of it is prototype design or aircraft design, just making a good aircraft that's balanced well. And the other hand of it is, hey, can you rely on automation to make up for a poor build, which this, as nice as it looks, isn't very good. It's a first attempt. So yeah, I think if you invested to develop a good version of this, you could probably use that approach. And then it would just come down to setting up your sticks right so you can provide gentle control. So you don't put it into dangerous parts of the flight envelope. Like to finish the thought, when I said this, there's real stress on us, like being patient with your control, but not too patient. It's a challenge of finding the right rate that you apply your force input, not your position. And when you let off the force input. And the difference there is that's like a really bad like S-curve heading control or a really slow, steady, oh, this is great, I'm flying great until you do this, and then you're sideways. Like that. So yeah.
Thank you.
Thanks. I guess wherever the microphone goes is whoever gets it first. So
can you speak to setting up Gazebo for a novel vehicle like this? Were you able to use your mechanical engineering knowledge and set it up easily using information for more typical vehicles, or was that a challenge to convince Gazebo to do what you need?
no, it's just a bit of a learning curve. But if you're patient and you have time, it's pretty easy to come up with like your inertial model and your geometry model in Gazebo, like through the SDF format. And then at that point, it's just setting up your, how it moves through space well. And then there are challenges with Gazebo. Like the primary issues with Gazebo is it does decent physics simulation, but it falls apart when you want like good friction models or like contact models between parts of your robot. So it depends on your application. But as a mechanical engineer, if you're trained and you understand this stuff, it's just a matter of trying to figure out how to convert it into the mathematical description for Gazebo.
So with reference to your comments about flying on stock ArduPilot, where did you mount the flight controller, or specifically the IMU?
Where's the IMU? It's on the wing.
Okay.
Is that what you're asking?
That's
Rob?
exactly what I was
Yeah.
asking.
So in fact, if you really think about it, when you're flying these bad boys, you're not flying the fuselage that moves underneath, you're flying the wing. So as long as you don't even really care what your fuselage is doing for the most part, you just want it to move your wing correctly. So my core research work from when I started before I became a drone engineer for whatever reason was on the learning system stuff. So this is a model-free control like ArduPilot, and I don't really care what the weight shift is doing when I'm controlling this with this controller. I just want the wing to stay up and stay stable. So what really matters for this controller design is sort of how you couple the information of the dynamic stability from, the reference dynamics with the IMU error or state error from the EKF, and then to control the wing. Thanks. Geez, busy crowd.
ありがとうございます。
はい
すごくリアルタイム、リアルと、シミュレーション、すごく興味あるんですけども、私は PC で SITL を動かす、SITL ですね、動かすと、OK、Not フライトコントローラーだと BAT という経験をしているので、 今、シミュレーションオンハードウェアを使ってテストをしています。で、もしそちらの方でシミュレーションオンハードウェアでの確認等されていたら、その辺のことをお聞きしたいなと思ってお聞きしたいです。以上です。
So you can't put the translation there. It's only going this way.
It's not good?
Well, look,
It seems like it's good, but
did
okay,
it tell you what he said?
roughly.
Oh,
He
okay.
doesn't care about real life. He only cares about games, which is a sentiment I can appreciate.
No, I think it doesn't work right. Actually, it's set up to go English to Japanese only, so it doesn't.
Oh.
It doesn't go back the other way. It does not.
Oh, so this is cooked.
Yeah, sorry. So, I think his question was that in his experience, he has, tried to tune in Siddle and then run it on a real vehicle and it has not worked. And then I think he said that you've had better experience, running Siddle on hardware and,
So like a flight controller hardware that's plugged into a simulation environment?
I guess so. Is that correct?
Don't ask.
もう一回最後の方、
あ
なんか、
えっと
ハードに、なんかフライコンにシミュレーターが動いています。
そう
動いてる
です。私は、キューブオレンジプラスにシミュレーションオンハードウェア
Yes,
をインストールして、
Yeah.
自分の作ったプログラムをテストしている。
yeah. So
Yeah.
he is running simulator on a Cube Orange plus light controller.
Yes.
And そっちの方がうまくいく。
Yes.
And he thinks that works better than running it just on your PC.
As software, okay. Yeah, listen, I haven't done that yet. I have my flight controller running next to my computer and then communicating. But I don't see why that wouldn't be the better choice for the flight controller side of the simulation, right? Like, to come to it, like at the end of the day, Gazebo doesn't care where your inputs are from. You just need to provide an input. So yeah, I haven't ran into issues with my flight controller software running poorly in simulation, like in Siddle. Really, my focus has been on the dynamic simulation side. So I want to highlight this slide here. It's a philosophy. It's saying, can I use simulation to replace real flight testing? Of course not, no. But if I refine my models over time as I collect more data and I improve them, eventually I'm going to come up with something that's closer and more useful to the real one. So in some sense, giving your dynamics simulation access to real flight controller hardware is probably the better choice, because it's what you're not modeling anything anymore. It's just the bloody real thing. Like, just use it. So I think that's a good approach. Is that a satisfying answer though?
Thank you. ありがとうございます。
No problem. My pleasure. I think there's two. There's Michelle and then one in the back.
Running a little short on time.
Yeah, I'm a whole hour almost. You're making me work, Randy.
Last question for Michelle.
So I was just wondering, because the manned ones are quite mechanically complex, whereas these ones, I was wondering how you did the mechanical part of it, because servos, I assume, would be not strong enough.
So the full size and the miniature have kind of two different development tracks for actuation. In the case of the full size, I didn't talk about it, but we can talk a bit more after if you like. In a nutshell, I used it's called a cable-driven parallel robot to provide me with like flexible admittance. So it can be stiff when I need it, or it can be a soft touch when I need it. And I find that works well for the large volumes of the full-size aircraft, rather than like a fixed link arm, which would be very hard and expensive to design for the application. So a cable-driven robot, if you think of like a sports stadium, like a camera gimbal set up on like big cables, it's basically that. And I can do that with just a set of like 4 actuators. So it's very cheap. In the case of the miniature model though, I cooked up this, you can't see it, but it's like, I call it a servo hang block that replaces the hang block. And it's an okay design. It definitely isn't the right design for the miniature. But the challenge is picking the right actuation scheme for the scale. So as you scale up, the servo hang block design that this one uses definitely would not be a good choice for the full size because you would need some crazy big and expensive servos for the small volume of the hang block. The hang block being the thing that joins the wing to the fuselage mass. In the full size, I'm using a cable robot. So in other words, I'm using different actuation schemes. And then what I'm trying to do is map my adaptive control action to be agnostic to what actuation scheme I'm using. So I don't care what actuation scheme, it just has to fly kind of the same, despite the scale difference. And so that's what this shows is an adaptive actuation scheme on the simulated version of aircraft.
Cool, thank you.
My pleasure. Okay, you want to wrap it up or do one more? Okay.